So on the IT side, for especially a lot of large organizations, that's their fear. Can I trust now this bioinformatics scientist that he's not going to run away, leave a while loop going on into infinity, and then we all wake up tomorrow and the state is bankrupt? All right, welcome everyone to the Bioinformatics Lab podcast. I'm Kevin Lipwit with Andrew Page. We're from Theogen, and today we're talking cloud computing to support all these crazy bioinformatics technologies we've been talking about on this podcast. And it's a huge topic, so there's a number of different avenues we can go. And I want to start off with maybe where the first interaction of cloud computing for a lot of bioinformatics scientists, and then the different layers in which you can implement cloud technology. Because I think a lot of laboratories are just thinking, hey, we need to migrate things to the cloud. If you're a bioinformatics developer, you're like, hey, just get me a cloud environment and I can do the things I needed to do. And I remember having that perspective whenever I was at the Virginia Public Health Lab, because more than even cloud, I just wanted a dev VM. I wanted something where I can be my own sysadmin. I can go and access resources, and it was in the cloud, so I can access things remotely, and that's really all I needed. But I would say that's kind of really just the first level of cloud computing, is getting some kind of virtual machine, as it were. But that's a good first step.
Absolutely, yeah. And first of all, Kevin, you're just waiting for to become a father for the second time. So, if you have to run off in the middle of this, then I think we'll all understand and wish you all the best for the future for the next 18 years. But yeah, cloud computing, my God, like it's evolved over time. Like I'm slightly older than you, and so I remember back in the day, it was like grid computing. It was like the first bit of cloud, where you could join up lots of computers and in a heterogeneous system, and then use the resources of those to tackle bigger and bigger problems. And then they came up with these terms, cloud computing, and it's evolved over time quite a bit. So you have your major systems like from Amazon and Google and Microsoft, and then you have obviously OpenStack, which originally came from Facebook, actually, or Meta. They did all the technology behind that, and then they made it open source. So you have a variety of different things, and so cloud is very powerful. So I guess my first experience of large scale bioinformatics was within clusters or on single machines, usually stuffed under a desk somewhere. Um, and it kind of worked. But what is applicable for maybe physics 30 years ago, giant cluster is not necessarily applicable for what we need in bioinformatics right now. And we have different needs. And even within bioinformatics, we have the micro community has very different needs to the human community or plants. And so, we have lots of a high volume of really small things, whereas say in the human world or the plant world, they have a few genomes and they're massive, absolutely massive. And so they have different requirements. We maybe if we do assemblies, we need small amounts of memory and, but lots of those individual ones versus say assembling a plant where you need just the most giant machines with terabytes of RAM. So cloud computing is great, I think, for, I guess, scaling in different ways to what we need.
I think that's a good point, in that it's going to depend, the way in which you set up your cloud infrastructure is going to depend greatly on your use case, right? Like, again, we talked about either VMs, and you started talking about like clusters and more sophisticated systems. Your cloud infrastructure could look really similar. Like, if you're a single developer, you have relatively low samples, a single VM may suffice completely. You might have a couple of local bash scripts that you put on there, and you just need your VM, a couple terabytes of memory, decent storage and CPUs, and you're good to go. But if you do have like really production scale volume, when you're getting samples, hundreds of samples a week and things like that, that single VM is really going to peter out quite quickly. And you need to set something up that looks more similar to an HPC cluster. And there are tons of resources on pretty much all the cloud providers that help you provision those resources. Because like I remember, yeah, again, like I was really just using the cloud in the beginning like another computer, like almost like it was another desktop. It's like, all right, I got another VM. I'm running out of space. Let me add more memory to my VM. And then I didn't realize how to scale things. But then once you start getting into the world of like batch concepts, like GCP batch, AWS batch, I think the Azure, they also call it batch. Then you're like actually submitting jobs and provisioning individual VMs for the analytical modules themselves. And it's like, that's when you are looking at things like scalability. And exactly to your point, there's a lot of resources that are already pre-built on these cloud platforms that meet the specific needs of different communities. Like Google, they had their whole Verily Life Sciences, and there's a whole pipelines API where it's based on helping to meet the needs of bioinformatics pipelines and making sure it's accessible to Cromwell and all the like there.
I don't know if you've ever been involved in procurement with large organizations or government or public sector. It can take a while. And what I like about cloud is that you can get the resources you need today or in 5 minutes. You don't need to wait 6 months or 2 years. You don't need to apply for funding, with 20 pages of documentation, or maybe even more. And then, you go through all the rigmarole, and then you get do you eventually put out tenders, for 12 weeks to make sure it's all competitive. And then you get, people to come in, they build it, they fit out data centers, they do all of that. And then they have to go and do all the setup. And then eventually, a year and a half later, you have your system and the resources you need. And because it's such a huge task, you'll actually go and buy those resources maybe 5 years in advance because you're buying physical hardware. You'll say, okay, well, for the next 5 years, I need this. I'm going to do it once, buy it, shove it in the data center. That's going to be turned on using electricity, and then we'll gradually burn through that over time. Whereas with cloud, you can just rent what you need right now. You're not renting for 5 years' time. And in 5 years' time, when you do need some resources like space or compute, it'll be probably 20% of the price, because prices come down all the time. So that's what I like about cloud. Actually, it does save a lot of money. It saves an admin. You get economies of scale because you're not running your own little data center, or within your university or whatever. It's off in some massive data center somewhere else, with probably hundreds of thousands of different, VMs running on thousands of computers, and you don't need to worry about it. It just magically runs. And that's what I love, And I think more and more we're going to move away from small local data centers or server rooms to this kind of model. There are certain cases where you don't want to do that. So say, I guess for if you have a sequencer, you want to pre-cache things sometimes locally, and then push them up. You don't want to say a nanopore device just streaming out content. Your network may not be stable enough for that, and that might be a bottleneck. So you want to kind of pre-cache and then push it up. But for everything else in bioinformatics, once it's in the cloud environment, it just makes everything so much easier.
That quick access is both like the strength on a lot of the practitioner side, but the fear on the IT side and procurement side. Because of that quick, low barrier to access, you essentially have an open tap. It's a credit card, you're signed up, and it's like, all right, I have my cloud resources. And so your charges are going to just be a factor of whomever's using and running the system itself. So on the IT side, for especially a lot of large organizations, that's their fear. Can I trust now this bioinformatics scientist that he's not going to run away, leave a while loop going on into infinity, and then we all wake up tomorrow and the state is bankrupt? You know what I mean? Because It's not like, AWS, GCP, all these cloud resources, they put in all these quotas and resources to make sure there's a bit of bumper before they fall into the gutter. But nonetheless, people can run away with cost. So that becomes that challenge. And especially in the conversation of procurement, that old model, which is for sure the legacy model, the reason it stood the test of time is because it was so controlled. It's like, I know what this lab is going to have for the next 10 years. But that's obviously not conducive to a field that works as quickly as we do. Even in terms of the types of compute resources laboratories have needed, if you were building your lab and your compute infrastructure, 3 or 4 years ago, maybe you were super heavy on CPU. And now we're in a world where it's like, hey, GPUs are massively important. If you're doing anything even on the base calling side, we're talking about a whole different hardware. NVIDIA, we're watching them just innovate on the space day after day after day. These like literal hardware concepts didn't exist or weren't in the psyche of like, bioinformatics IT admins, 3 or 4 years ago. So you're just going to be outdated if you have a system that's meant to be static for 10 years time.
Absolutely. And yeah, like on the GPU side, definitely you can rent those in the cloud. Um, and what I like about it is that GPUs are changing all the time. Like they're getting more and more powerful and cheaper. There's a huge amount of innovation there. And you're not going to buy like a really expensive GPU right now today and then find in 6 months' time it's out of date and whatnot, because you can just rent the latest ones, if you need to. And then, with the wider adoption of GPUs and more software, it's kind of created this, I suppose, ecosystem. It's got critical mass. So then that you can be confident as a software developer that you can go and actually program in these frameworks, because it does require a different way of doing things, and not every task is applicable to that kind of parallelization. But, many of them are, and particularly for what we do, often, we'll take in, say, reads, 1 million reads or 10 million reads, and we'll do the same things to them. And that's, ideal for a GPU, doing the same thing over and over and over again. Whereas if you need to stream things in a different way, then CPUs are actually a lot better. So, yeah, it's kind of cool with the cloud. You can just spin things up. And what I like actually is there's so much competition as well between AWS, which is Amazon, and Azure, and Google, GCP, that it drives the prices down. And no one is, going and ripping you off, because you can just jump very quickly. You can see the prices there and then. You can see how much it costs to store a terabyte of data, and if you can just disappear off. And so they are conscious of that, and they lower the prices, and it's cutthroat out there, and it's awesome for the consumer.
Absolutely. Okay, let me ask you this, and this is something we've had to start even making sure we keep an eye on internally over here at Theogen, but you talked about access to all these latest technology, hardware, scalable compute. Like, you're a kid in a candy shop as a developer when you have a cloud access here. But of course, curbing the costs and making sure things don't run away. Can you speak to your experience of everything we've been trying to do in terms of dashboarding, alerts, and all the rest on what would you recommend laboratories do when, hey, they're met with that pushback of like, hey, wait a minute, I don't want you to run this build and run this lab to the ground because you got the new NVIDIA chip running and you forgot to turn it off.
Yeah, I mean, it's a double-edged sword. As you say, people can go and spend a lot of money very quickly, and people do, unfortunately. And, we've made mistakes and stuff like that as well. And you learn the hard way, unfortunately. So you can put in extra logging so that you can catch things after the fact. You can put in limits. But ultimately, you need to, I guess, limit the access and limit the danger to yourselves as well, as much as possible. It's difficult because you do have to trust people. And maybe it is just a case of you don't allow anyone who you don't trust in. But if you consider the cost going the other way, like, if you want to build a data center, it's going to cost you tens of millions these days, if you want a standalone data center, which is kind of the bog standard. So, tens of millions of dollars just for an empty building. And then, you got to fit it out, and you got to put in, probably water cooling these days. And, you actually have to put computers in there. Usually people want to put new computers in, not old computers, into a data center. Say if it's water cooling instead of air cooled, you obviously need actually to go and buy new ones. And then you have all the costs of running it, and then you have to have physical people there on site maintaining it. And so, you're into a couple million a year just for keeping that building running, even if it's not doing anything. And then you have system administrators on top of that, to actually manage the software. And then you have, the bioinformaticians eventually on top of that. And so that's the traditional way of doing it, say within a university or government, but it's horrifically inefficient. And those costs are hidden because they happen in big chunks, probably with government money, capital expenditure here, and they say, oh, well, we'll write this off over 20, 30 years. And, so they kind of hide a lot of the costs, but if you actually drill it down and say how much does that cost, it's going to be a fair whack of money for what you actually get compared to the cloud, where you have vast economies of scale. you don't have to worry about, the security guard walking around, keeping it safe. You don't need to worry about the cooling, electricity, whatever. It's just magically happening in the background and you're given a single price. And often I see people trying to justify buying versus renting, so cloud versus on-prem. And they'll kind of forget about the cost of the building. They'll forget about the time lags and the people required. They'll just focus on maybe the electricity cost, the extra operational costs. Um, so yeah, cloud computing is just so different and so great.
That's a good way to poise it too, of like the costs associated with all the on-prem facilities required to maintain that versus the cloud resources, even in the face of threats of like runaway compute jobs and things like that. You might have to learn
Yeah.
$100 lesson or $1,000 lesson every now and then, but like put in perspective of a tens of millions of dollars investment, that's a pretty cheap lesson to learn. So like, yeah, I think that's a
Yeah.
good perspective to have.
And then you have other things like fire, and disaster
Yeah,
recovery. And like, do you need two data centers? Um,
insurance on
and
it.
this
Yeah,
is legitimate questions that people ask, what happens? And, you obviously you have all your say, you've got generators usually, you've got electricity coming in from two sides, you've got data coming in from multiple sides. And then, if you really need high redundancy, you have to duplicate everything in two buildings or have offsite tape backup, and it's expensive, Whereas for me,
tape
right,
backup.
it's cheap. Um, like for me, if I can just say, oh, I want to have this in Berlin and this in the UK in London, and that's all I have to worry about. I know that physically the data is copied in two different spaces, and if there's a fire, I'm fine, or a flood, or whatever. And these things do happen, People talk about, say, fire suppression systems or whatever in data centers, gas. But the reality is things happen, or someone drives a truck into the data center accidentally, or I don't know, there's a flood or an earthquake, a tree falls on it. These are all real life examples.
Absolutely. And, it's kind of crazy just wrapping things up here too. Cloud computing, I think for the whole episode, we've been pretty hardware informatics focused, but that's really the reality of, I think, a lot of bioinformatics scientists is being able to learn this vocabulary, this infrastructure, because it's going to be a massive part of what they need to do. Yeah, go ahead.
Yeah, sorry, I'm just thinking of stories now from when I was in the Sanger Institute. They have this
Please.
huge, big data center. It's like an ice cube. It looks like an ice cube. And, they're talking about risks, right? And there's a local World War II airport where they do all of these flyovers, for World War II aircraft, regularly, your B whatever bombers and your Spitfires. And they use the big cube as a visual reference to fly over, to turn around. And one of the scenarios is like, well, what if one of these aircraft, as they fly over regularly, crashes? Because these aircraft are, 80 years old. Uh, and that's a problem. And then, another time was they had a power outage and the generators didn't come on, and it was because the diesel for the generators required an electric pump because it was higher. Sorry, it was lower down. The generators up here, and then the tank was down below, and so they discovered this the hard way. That all their systems that they'd carefully planned failed because of gravity.
There you go. That's the final piece of argument people need to their IT. If they're trying to suggest building on-prem, you could say, wait a minute. What about the World War II planes that may potentially crash and burn our systems down? We must go cloud. All right, man. This is definitely going to be a topic we continue talking about on end or continuously on the podcast. So I think we can wrap it up things there, unless you wanted to say anything else.
I just good luck with becoming a father for the second time. It's a great place to be in.
Absolutely. I appreciate it, man. And we'll see everybody in the next one. Cheers.
Good luck.